Okay, so I think I'm supposed to give a little talk, and this is really a warm-up for the next talk by Noah Kravitz. So in March, I had posted a paper on arXiv and gave a talk in the New York number theory seminar about multiplicity vectors and multiplicity matrices. And this is something that came up in trying to understand what is called the Boudin-Fourier theorem and the theory of equations, which is something that gives an estimate for the number of real roots of a polynomial in a finite interval. And when one talks about the roots or the zeros of you take a non-zero polynomial f of x with real coefficients, and we say the root has multiplicity mu, you can write f of x, multiplicity mu at a number lambda. If you can write f of x as x minus lambda mu times some polynomial g of x, where g of lambda is not zero, and if lambda is not a root, we just say it's a root of multiplicity zero. And so you take your polynomial degree n, you let fj of x be the jth derivative of f of x. You pick your favorite real number lambda, and then you evaluate lambda at all of the derivatives of the polynomial, and let uj be the multiplicity of lambda as a zero of the jth derivative. So this vector, m sub f of lambda, it's an n+1 dimensional vector with non-negative integral coordinates. And we call this the multiplicity vector of the polynomial at lambda. So the muj is just the multiplicity of lambda as a root of the jth derivative. And that's what it is. So for example, if you take polynomial x cubed minus 3x squared of degree 3, these are the derivatives. If you take lambda equals 0, it's a root of multiplicity 2 for f, multiplicity 1 for f prime, and multiplicity 0 for f for the second and third derivative. So this is the multiplicity vector of 0 for this polynomial f. The multiplicity vector for f at 1, well, 1 is a 0 of the second derivative and only for the second derivative. So we have this multiplicity vector, and so on. So 0, 1, 2, and 3 are the only lambdas that are roots of any of these derivatives. And for any lambda not 0, 1, 2, or 3, the multiplicity vector is 0. So that's the multiplicity vector. You can get interesting sequences of numbers as the multiplicity vector. Here I took random, more or less, polynomial degree 5. You look at its derivatives. The multiplicity vector is 0. So 0 is a root of f of x of degree 3, of multiplicity 3. So you have this multiplicity vector. If you look at lambda equal 1, it's a root of f of x of multiplicity 1. It's not a root of the first derivatives, but suddenly it pops up again as a root of the second derivative of multiplicity 1. So you get this multiplicity vector. And one can ask a simple question for which there's a simple answer, which is what multiplicity? So if you take the Taylor expansion of your polynomial around lambda, then the jth coefficient, the jth Taylor coefficient, is essentially the jth derivative at lambda. So you have so lambda is a root of the jth derivative if and only if this jth Taylor coefficient is 0. And it's also the case that f of lambda c naught, but the nth derivative at lambda is never 0 if you have a polynomial degree n. So that part we don't need. So a multiplicity vector is a vector with non-negative integral coordinates with the property that, first of all, the nth derivative is always the last coordinate, which is the n plus fifth coordinate. This last coordinate is always 0. And if some uj is at least 1, then the next coordinate, u sub j plus 1, is 1 less than u sub j. So any multiplicity vector for a polynomial at a point lambda will satisfy these conditions. And it's easy enough to check that for any multiplicity vector, it is always the multiplicity vector of some polynomial degree n at lambda. Let's see. So if you want to know what multiplicity vectors are multiplicity vectors of polynomials at a point lambda, the answer is all of them. Whenever you have a multiplicity vector and you pick a number lambda, you can write down a polynomial f of x, for which that multiplicity vector is the multiplicity vector at that point. So this becomes interesting when we try to look at the multiplicity vectors of a polynomial at 2 or more points. So we say that f of x be a polynomial of degree n, that fj of x be its jth derivative, and take a sequence lambda of m plus 1 distinct real numbers. And for each real number lambda sub I, the polynomial f of x is fixed. It's a fixed polynomial of exactly degree n, not degree n minus 1, degree n. And so you can take the jth derivative for j going from 0 to n, and you let mu ij be the multiplicity of lambda I as a root of the jth derivative. So this gives us an m plus 1 by n plus 1 matrix. So each row of this matrix is the multiplicity vector of the polynomial f at the corresponding lambda, lambda 0, lambda 1, up to lambda sub n. So the ith row of this matrix is the multiplicity vector of the polynomial f at lambda sub I. So for example, here's the quartic polynomial x to the fourth minus 4x split q plus 4x. I take lambda to be the set of just the numbers 0 and 1. So one can check or assign it to your calculus class that the first row of this matrix is the multiplicity of 0 as a root of the derivatives of f. And the second row is the multiplicity of 1 evaluated at the derivatives of f. So this 2 by 5 matrix is the multiplicity matrix for this perfect polynomial. So this tells us something about the interactions between the zeros of a polynomial. That's sort of the idea of this. So the definition of this multiplicity in muij says that for all j, for all derivatives, for all j from 0 up to m, I think it should be an m here. The jth derivative is g sub j of x. So lambda I is the root of multiplicity mu sub ij. So the jth derivative is of this form. And this is exactly right. So I have m plus 1 numbers, lambda 0, lambda 1 to lambda sub m. They're distinct numbers. X minus lambda I is the root of multiplicity mu ij. So fj of x factors in exactly this form, where this gj is non-zero for all of the lambda sub i's. And if f has degree n, then the jth derivative has degree n minus j. So the sum of the mu ij's cannot be bigger than n minus j. So we have this constraint on the columns of any multiplicity matrix that you look at the jth column sum, ui j I goes from 0 to m. This is the jth column sum. It's at most n minus j for every one of the n plus 1 columns in this matrix. You can also observe, of course, that if you take your polynomial and you multiply it by a non-zero number, you don't change the multiplicity of any root. So it's enough to consider just monic polynomials. So in general, one can define a multiplicity matrix as follows. In my notation, it's n plus 1 by n plus 1. It's an n plus 1 by n plus 1 matrix written like this, these are the muij's, with the property that every row is a multiplicity vector. That means the coordinates are non-negative integers. And if you have a positive integer in some place in a row, the next coordinate to the right is strictly one less. The last coordinate in every row is 0, and each column sum is at most n minus j. So that is a multiplicity matrix. So this is a multiplicity matrix. Each of these rows is a multiplicity vector. The column sum here is at most 0, at most 1, at most 2, and at most 3. And this very nice matrix, each row is again a multiplicity vector, but it's not a multiplicity matrix because the column sum here is 2 and it's at most 1 in the multiplicity matrix. So there are two simple problems. One is the following. Suppose you're given a multiplicity matrix. So you have these muij's, and you're also given a fixed sequence of n plus 1 distinct real numbers. Is there a polynomial of degree n for which this matrix is the multiplicity matrix evaluated at these n plus 1 points? And the related question is, given a multiplicity matrix, can you find a polynomial of degree n and some sequence of distinct real numbers? So you can pick your real numbers to depend on the matrix, such that this matrix is the multiplicity matrix of the polynomial f at the sequence of points lambda. So those are two nice questions. So the simplest case is when you are just looking at a matrix with 2 rows. So this is a multiplicity matrix. So each row is a multiplicity vector. The column sums at most 0, at most 1, at most 2, at most 3. Suppose I take lambda to be the 2 real numbers 0 and 1. Is this a multiplicity matrix of some polynomial, of some cubic polynomial, of course, right? This is a 3 plus 1 by 1 plus 1. It's a multiplicity matrix. Is it a multiplicity matrix of some monic cubic polynomial? So the first row is 2, 1, 0, 0. So if this is, so any cubic polynomial which has this as its multiplicity vector at 0 must be of the form x cubed plus ax squared. So the cubic polynomial has to look like x cubed plus ax squared with some a. But we also have the second row. This is the multiplicity vector of lambda equals 1. And there's a simple root for the first derivative. And the only cubic polynomial that has this as its multiplicity vector must be of the form, so the Taylor series has to look like x minus 1 cubed plus b times x minus 1 squared plus c for some b and c. So you multiply this out, so you have a polynomial of this form, which has to be a cubic polynomial of this form. And when you equate the coefficients and solve for a, b, and c, you actually get some numbers. So in fact, there is a unique polynomial, a unique monic cubic polynomial, which has this guy as its multiplicity matrix. That's nice. Let's see, here's another example. So this is a 2x5 matrix. This would have to be the multiplicity matrix of a quartic polynomial at 0, 1. So so the multiplicity matrix, so this is the multiplicity vector at 0. This is the multiplicity vector at 1. And the multiplicity vector at 0, this guy, that means it has a root of multiplicity 3 at 0. It has to look like this. And if you look at, oops, where is it? And if your quartic has a multiplicity vector like this at lambda equal 1, then the polynomial has to look like this, which you expand. And again, so this is the Taylor series at 0. This is the Taylor series at 1. You equate coefficients and you solve. And what you get is that -6 equals -2, which tells us that this multiplicity matrix is a perfectly legitimate multiplicity matrix, but it's not the multiplicity matrix of a polynomial. Let's see what this thing says. So, I mean, there are various conditions that tell us. So this says, so for example, here's a multiplicity matrix. Suppose I take the set of m+1 real numbers 0 to m, and I take another set of m+1 numbers, which are some strictly increasing arithmetic progression, then this is the multiplicity matrix for a polynomial f with respect to this set, if and only if there exists another polynomial, and this is the multiplicity matrix with respect to this arithmetic progression. And there are a number of results of that sort. In particular, if you're only looking at matrices with 2 rows, any set of 2 different numbers is an arithmetic progression. So for matrices with 2 rows, it's a multiplicity matrix for a polynomial with respect to some set lambda, if and only if it is with respect to just the number 0, 1. So for 2-row matrices, you only have to look at 0, 1. Let's see. So this is a multiplicity matrix of this form. So this is not the multiplicity matrix. This is not a multiplicity matrix. I'm not sure I even wrote this because here the column sum is 3 and it can be at most 2. This is more interesting. So this is, suppose you have a multiplicity matrix of this form. The column sums are at most 0, 1, 2, 3, and so forth, but there is no polynomial for which this is the multiplicity matrix. This is in fact what one of the things that Noah Kravitz will be talking about in a few minutes. So let me just state what our, restate the most interesting questions here. If you have an m+1 by n+1 multiplicity matrix, and you're given a fixed sequence of n+1 distinct real numbers, can you construct a polynomial, or when can you, for what multiplicity matrices and sequences lambda, can you construct a polynomial of degree n, for which this is the multiplicity matrix of the polynomial? And the second problem is, if you're given the multiplicity matrix, can you construct a sequence of m+1 real numbers and a polynomial of degree m, such that this is the multiplicity matrix of this polynomial evaluated at these numbers? This is Suppose I take these these sets of numbers 0, 1, 2, and 0, 1, 3. Can you find a multiplicity matrix with this property? There is a polynomial degree n for which the matrix is the multiplicity matrix with respect to 0, 1, 2, but not 0, 1, 3. And more generally, and this is the way I think of this problem, is you have a polynomial and we want to try to describe or discuss what you might call the forbidden interactions between the roots of the polynomial. That is the general statement. And I think if in my note that is on archive, there are a number of additional problems that are similar to that. In any case, all this came out of just trying to understand this ancient theorem of Boudin and Fourier on estimating the number of roots of polynomials. And some of these questions are answered by Noah Golan, Noah Kravitz, and Kevin O'Brien in a paper which I think was posted on archive yesterday, and that I think Noah will talk about. So with that, I thank you.
All right.
I'm done. Let's see.
Okay. Do you take questions?
Oh yeah, there's always time for questions.
Okay. So maybe you mentioned it, Mel, but why you only consider real roots? What about complex roots?
So there is absolutely no reason not to consider complex roots. The reason I discussed only real roots is because life is short and time is incompressible. And I started thinking about this. I don't know exactly why. I've actually forgotten why I became interested in just trying to understand these classical theorems of Descartes, Boudin, Fourier, Sturm's theorem, other things connected with what is sometimes called real algebraic geometry. But there's actually no reason not to consider complex roots and complex multiplicities. I just haven't had the time to do that, and I haven't finished even writing up some of the stuff that I've done in this theory of equations bit. So,
yeah, I guess for complex roots, if we still consider real coefficient polynomials, then they always appear in pairs, right? So yes. Then probably there will be some repetitive in the matrix.
Right. I mean, yeah. I mean, like the key fact when you're dealing with complex roots of real or complex polynomials is the Gauss-Lucas theorem, which says if you have the roots of the polynomial, then the roots of the derivative are always inside the convex hull of the roots of the original polynomial. So you have this localization of the roots, and but I really haven't thought very much about this yet. But it's on the infinitely long list of things to do. That's one of them. But that's
okay.
all.
Thank you.
No reason not to have done it. But again, the motivation was just to try to understand something about the distribution of real roots of polynomials. That's how I had started this, and just trying to understand these ancient theorems that they teach you Descartes' theorem in high school without a proof. And I'd be curious if anyone went to a really good high school, which not only told you Descartes' theorem, but tried to prove it for you.
Okay, that's a lucky one. Yeah. Okay. Thank you. Yeah.
Okay, Noah, you are on in 5 minutes, and when you are ready, you can practice screen sharing and